In this lesson, we'll discuss learning target number 4, determining the percent yield of a reaction and discussing possible sources of error in experiments. The amount of product created in a chemical reaction is often less than expected using stoichiometry. This can be caused by several real-life problems. There are always situations when performing an experimental procedure when you'll lose some of your chemicals. Some examples include using a stir rod. When you introduce a stir rod into a beaker and then remove it, you will lose some chemical residue. This also happens when you're transferring your chemical from one container into another, like when you're measuring. Now, it's really important when experimental procedures are designed that this error is minimized, but it can never be totally removed. And it's your job as a proper chemist to try and reduce this error as much as possible. Another source of error is that we can never buy 100% pure chemicals. And even if we could, they'd only be 100% pure when they were sealed in the original package. As soon as we open the lid, some impurities can enter in. The purity of a chemical is actually listed on the chemical label. We buy lab-grade chemicals, so they're anywhere between 96% or higher when they're originally purchased. Sometimes you can have side reactions occur as well, where you form an undesirable product. For example, making CO2 instead of making CO. Or having poor reaction conditions where your chemicals take so long to react, you think the reaction is over before it's really not. To calculate how efficient you are when performing a reaction, you can calculate your percent yield. In order to do that, you take the actual yield, which is how much of the product you actually recover, divided by your theoretical yield. The theoretical yield is just a fancy way of saying, what does stoichiometry predict if everything runs perfectly during your experiment? Let's do a couple of examples. Example 1 tells us how much of a reactant we're going to use. 169.3 grams of zinc iodide, and we're going to react that with extra sodium phosphate. It tells us what our actual yield is. If we collect 57.2 grams of precipitate, what is the percent yield of the reaction? They don't give us a balanced chemical equation, so let's start there. This looks like it's going to be a double displacement reaction. Let's see what proof we have. Because zinc phosphate is a solid, this is going to be a double displacement precipitation. I'm going to make this into an organization chart and include the numbers given in the question. I'm given the actual yield of the precipitate made. I need to find the theoretical yield using a stoichiometry question. I'm going to take my 169.3 grams and figure out how many grams of zinc phosphate would theoretically get made. My first step is to take my mass and divide by the molar mass of zinc iodide. That works out to be 319.21 grams per mole. Now that I'm in moles, I can convert that using a mole ratio into my zinc phosphate. I'm going to have a 1/3 mole ratio. In order to change this into grams, I'm going to times this by the molar mass of zinc phosphate. My theoretical yield equals 68.271 grams. I'll keep 5 digits in here and round to the proper sig digs at the end of my calculation. Now I take my actual yield and theoretical yield to calculate the percentage. Now I need to round for sig digs. The mass of the zinc iodide originally had 4 sig digs in it, but the actual yield of 57.2 grams has 3, so I need to round this to 3 sig digs. This means that I was 83.8% efficient when doing this reaction. I was expecting to get 68.3 grams of precipitate, but when I performed the reaction in real life, I only got 57.2. Some experiments have been done so often that their percent yields have been published, and you can look them up online or in a table, such as in example 2. If you know the percent yield of a reaction and how much of a reactant you're going to start with, you can determine how much is actually going to be made. Or, if you're looking for a particular amount of product, how much of the reactant you should begin with. In these types of questions, you will still need to be able to figure out the theoretical yield using stoichiometry. Pause the video here and try out the question. Here's the answer to example 2. I'm going to start out by writing the balanced chemical equation and creating an organizational chart. I'm told in the question that 26.7 grams of H2CO3 is going to be heated in a decomposition reaction. I want to find the actual yield of water that's made. If there's a 76% yield for this reaction. I start by determining the theoretical yield for water. I take my 26.7 grams and divide it by the molar mass to change this into moles. I can then do a mole ratio into water. It's going to be 1/1. So I'm going to make 0.43043 moles of water. To change that into grams and determine the theoretical yield, I'm going to multiply by the molar mass of water. To determine the actual yield, I'm going to plug in what I know into the percent yield calculation. I'm told that the percent yield is 76.0. I want to determine the actual yield, and I know the theoretical is 7.7564 grams. I then rearrange this equation for actual. I'm going to have to divide both sides by 100 to get rid of this, and times both sides by my theoretical yield to isolate the actual. When I do that, my actual yield equals 5.8949. I should only include 3 sigdigs, so my final answer will be 5.89 grams of water being made. Try out the practice problems listed on the assignment checklist for percent yield.